All right, let's just jump right in. The device you're watching this on right now, it's not just a gadget. It's a whole universe of innovation, and it tells a story that literally starts with sand and ends up with the software that pretty much runs our world. Today, we're going to peel back the layers on that secret journey.
I mean, to really get a handle on just how fast this revolution has been, you have to hear this quote. It's such a powerful analogy because it shows we're not just talking about small little improvements over time. No, we're talking about a complete rewriting of the rules of what's possible, at a speed that's frankly unlike anything else in human history.
And you know, this progress isn't some abstract, far-off idea. It is in your car, making it safer. It is the phone that's probably in your pocket right now, connecting you to basically the entire planet. It's the web, it's search, it's even mapping our own DNA. All of these things were pure science fiction just a generation or two ago. So yeah, this isn't something that just happened in the past and is now over. We are living right in the middle of a revolution that's still going on. Which brings us to the big question. How on earth did we build this new world?
Well, everything has to start somewhere, right? You've got to build the physical engine that drives the whole thing. But what's it even made of? And how does it come into existence? Let's get into the actual physical foundation of it all.
Believe it or not, this entire journey starts with one of the most common things on the planet, sand. Yep, sand is where we get silicon from. We're about to go from that basic raw material to one of the most ridiculously complex objects humanity has ever created.
So check this out. This image maps out that incredible transformation. You start with this thing called a silicon ingot, which, let's be honest, looks like a giant metal sausage. That ingot gets sliced into these super thin, perfectly round wafers. Then, those wafers go through a crazy process with chemicals and light to etch these unimaginably complex patterns onto them. And those patterns are the circuits.
So what are we actually looking at in those patterns? Well, at the very, very bottom of it all, you have transistors. A transistor it's really just a microscopic switch. It can be on or it can be off. That's it. On its own, pretty simple. But when you arrange them in clever ways, you can do basic math. And the real magic happens when you use billions of them. And that is exactly what an integrated circuit, or an IC, is. It's a single chip, sometimes called a die, that crams all those billions of tiny transistor switches together. This incredible shrinking act is what Gordon Moore famously predicted, and it's what led to this absolute explosion in computing power.
And this is what you get at the end of all that. This is a processor die, the brain of something like your phone or a tablet. And doesn't it just look like a bizarre futuristic city map? You can literally see the different neighborhoods. The main processors here, the specialized areas for graphics, for memory. It's an absolute marvel of organized complexity.
Okay, so we've got this stunning piece of hardware. But right now, it's basically a really, really fancy rock. It can't do anything until we tell it what to do. So the next big puzzle is communication. How do we speak to the silicon?
Just think about that for a second. We think in words, in logic, in creative ideas. The chip? It only knows two things, on and off, ones and zeros. So how in the world do you bridge that massive gap? Well, this solution is pretty ingenious. It's all about translation. A programmer writes in what's called a high-level language, something like C, that's readable for a human. Then, a special program called a compiler acts like a translator, turning that into a lower-level language. And finally, another program called an assembler finishes the job, converting everything into the pure ones and zeros, the only language the hardware actually gets.
Now, the only reason any of this is even possible is because of this one giant, powerful idea called abstraction. It's a simple concept. At each level, you get to ignore the mind-blowing complexity of the level below you. A programmer doesn't have to think about transistors, and you don't have to think about code just to use an app. It is the master key to all of modern computing.
So once we have the hardware and we have the software to talk to it, what happens next? Well, the computer itself starts to change dramatically. We go from machines that filled entire rooms to devices that can fit right in our pockets.
Just look at the difference here. It is absolutely wild. On the left, you've got ENIAC from 1946. It was 80 feet long, filled a whole room. On the right, a personal computer from the 70s that could sit on your desk. This one picture tells you everything you need to know about the power of making things smaller.
Okay, now let's put some hard numbers on what you just saw, because it's even crazier. This table shows the performance you get for the same amount of money over time. Let's just say in 1951, the performance was 1. By 1975, with integrated circuits, it was 900 times better.
Okay, but by 2013, it was 250 billion times better. I mean, the numbers are so big, they're hard to even wrap your head around.
And all that progress, all that power and miniaturization leads us right here to what people call the post-PC era. You see it on the chart. PC sales are kind of flat, but then whoosh, smartphone and tablet sales just explode. The engine of computing had finally gotten so small, so powerful, and so efficient that it could leave the desk and just go everywhere with us.
So when you take a step back and look at this whole journey, you see how these different layers of technology, from the physics of silicon to the logic of software, have just completely re-engineered the world we live in.
So the next time you tap your screen or swipe or click, just remember what's happening. It's not a simple action at all. It is the final, visible step in this massive, mostly hidden journey. A chain of human ingenuity stretching all the way from a grain of sand to a chip of silicon to the software on your screen.
And that really leaves us with one last big question to think about. We've seen how yesterday's science fiction became today's normal. So what happens when the next wave, things like true augmented reality glasses or cars that actually drive themselves, what happens when they make that same leap? If this journey has taught us anything, it's that the future is probably going to get here a whole lot faster than we think.